Well, you have done it. We are in the last module. Great job. So we're going to be starting module 12.1, inference for linear regression. So we're going to go back and hit a little bit about lines of best fit and that kind of stuff. So when a scatter plot shows a linear relationship between a quantitative explanatory variable x and a quantitative response variable y, we can use the least squares line fitted to the data to predict y for a given value of x. If the data are a random sample from a larger population, we need statistical inference to answer questions like these. Is there really a linear relationship between x and y in the population, or could the pattern we see in the scatter plot possibly just happen by chance? In the population, how much will the predicted value of y change for each increase of 1 unit in x? What's the margin of error for this estimate? And in section 12.1, we will learn how to estimate and test claims about the slope of the population of the true regression line that describes the relationship between two quantitative variables. All right, so back in Module 3, we examined data on the eruptions of the Old Faithful geyser. Below is the scatter plot of the duration and interval of the time until the next eruption for all 222 recorded eruptions in a single month. The least squares regression line for this population of data has been added to the graph. It has a slope of 10.36 and a y-intercept of 33.97. We call this the population regression line or true regression line because it uses all of the observations that month. So suppose we take an SRS of 20 eruptions from the population and calculate the least squares regression line. Don't forget, for this regression line, you have to have y hat, the predicted value. So y hat will equal a plus bx for the sample data. How does the slope of the sample regression line, also called the estimated regression line, relate to the slope of the population regression line? So here you can see some figures below that show the results of taking 3 different simple random samples of 20 Old Faithful eruptions in this month. Each graph displays the selected points and the least squares regression line for that sample. So here down below you can see the population and the samples going on. It looks like they put them in blue. So what do you notice? Notice that the slopes of the sample regression lines, negative 10.2, 7.7, 9.5, vary quite a bit from the slope of the population regression line, 10.36. The pattern of variation in the slope B is described by its sampling distribution. So the confidence intervals in significant tests about the slope of the population regression line are based on the sampling distribution of B, the slope of the sample regression line. So this software, Fathom, was used to simulate choosing 1,000 simple random samples of n equals 20 from the Old Faithful data, each time calculating the equation of the least squares regression line for the sample. So here are all the values of the slope for the 1,000 sample regression lines, and they are plotted. Describe this approximate sampling distribution of B. What does this look like? Hopefully you're all thinking normal. It looks pretty normal. It looks pretty symmetrical. So a normal probability plot of this sample regression line slope suggests that the approximate sampling distribution is close to normal. Okay. The center, the mean of the 1,000 B values, and this is going to be 10.32. That's really, really close to what the population, the true slope was of 10.36. The spread, the standard deviation of these is 1.31, and later we're going to see that the standard deviation of the sampling distribution B is actually 1.3. So, pretty good. So the slope B and intercept A of the least squares regression line are statistics. That is, if we calculate them from the sample data, these statistics would take somewhat different values if we repeated the data production process. To do inference, think of A and B as estimates of unknown parameters, alpha and beta, that describe the population of interest. Suppose we have n observations on an explanatory variable x and a response variable y. Our goal is to study or predict the behavior of y for given values of x. Linear. The true relationship between x and y is linear. For any fixed value of x, the mean response mu sub y falls on the population true regression line mu sub y equals alpha plus beta x. The slope b and intercept a are usually unknown parameters. Independent. Individual observations are independent of each other. And normal. For any fixed value of x, the response variable y varies according to a normal distribution. Equal variances. The standard deviation y, or sigma, is the same for all values of x. The common standard deviation, sigma, is usually an unknown parameter. And random. The data come from a well-designed random sample. All right, the figure below shows the regression Okay, I don't know what that sound was for. The figure below shows the regression model when the conditions are met. The line in the figure is the population regression line, mu sub y equals alpha plus beta x. So here you can see for any fixed x, the responses y follow normal distribution with standard deviation of sigma. Just kind of seeing it all with the 3 dimensions. Kind of cool. For each possible value of the explanatory variable x, the mean of the response mu sub y given x moves along this line. The normal curves show how y will vary when x is held fixed at different values. All the curves have the same standard deviation, sigma, so the variability of y is the same for all values of x. The value of sigma determines whether the points fall close to the population regression line, a small standard deviation, or they're really wide and scattered, which you would have a large standard deviation. Okay, so how to check the conditions for inference. You should always check the conditions before doing inference about the regression model. Although the conditions for regression inference are a bit complicated, it is not hard to check for major violations. Start by making a histogram or normal probability plot of the residuals and also a residual plot. Here's a summary of how to check the conditions. Linear, independent, normal, equal variance, and random. Linear. It's almost linear, but linear. Kind of a little mnemonic device to help you. All right, so here's an example. The helicopter experiment. Students from Mr. Rose's class randomly assigned 14 helicopters to each of 5 drop heights: 152 centimeters, 203 centimeters, 254 centimeters, 307 centimeters, and 442 centimeters. Teams of students released the 70 helicopters in a predetermined random order and measured the flight times in seconds. The class used a Minitab software to carry out a least squares regression line analysis for these data. A scatter plot, residual plot, histogram, and normal probability plot are all shown below. So let's look over these. The linear, right? So linear, the scatter plot shows a clear linear form. And then you can see the residuals are all centered around 0. And then over in the residual plot, you can see a random scatter plot about the horizontal line. Normal, the histogram of the residuals is a single-peaked unimodal and somewhat bell-shaped, so it looks very normal. Equal variance, the residual plot shows a similar amount of scatter about the residual x, or residuals equal 0, okay, for all of those drop heights. So flight times and the corresponding residuals. They seem to vary more for the helicopters that were dropped from a height of 307. can definitely see that there, right? Independent, because the helicopters were released in a random order and no helicopter was used twice, knowing the result of one observation should give no additional information about another observation. And random, the helicopters were randomly assigned to the 5 possible drop heights. So, except for that slight concern about the equal variance, the one that we circled there, we should be safe performing inferences about this regression model in this setting. So now with estimating parameters, when the conditions are met, we can do inferences about the regression module mu sub y equals alpha plus beta x. The first step is to estimate the unknown parameters. If we calculate the least squares regression line, the slope b is an unbiased estimator of the population slope beta, and the y-intercept a is an unbiased estimator of the population y-intercept alpha. The remaining parameter is the standard deviation sigma, which describes the variance of the response y about the population on the regression line. So we're going to use our slope and our y-intercept, but we have to figure out what we're going to do for the standard deviation. So in that least squares regression line computed from the sample data that estimates the population regression line. So the residuals estimate how much y varies about the population line. Because sigma is the standard deviation of responses about the population regression line, we estimate it by the standard deviation of the residuals. So here you have this formula. Whew. All right, so let's look at this example after the bell. Okay, the helicopter experiment computer output, so there's a little computer Minitab output here, from a least squares regression analysis on the helicopter data for Mrs. DeRosa's class is shown below. So let's see if we can identify everything from here. Here I can get my least squares regression line. We've talked about that from different modules. So here I can see that the slope beta of the 2 regression lines says how much the average flight time of the paper helicopters increases when the drop height is increased by 1 centimeter. So remember, it's change in y over change of x. And here I can see that b is 0.00572444, and that's going to estimate the unknown beta. We estimate that on average the flight times are going to increase about 0.00572444 seconds for each additional centimeter of dropped height. All right, so that was our slope. So now our y-intercept. So we needed the y-intercept to draw the line and make predictions, but it has no statistical meaning in this example because look at this is negative. So no helicopter was dropped. You couldn't go below, okay? So we might expect the actual y-intercept alpha of the 2 regression line to be 0 because it should take no time for a helicopter to fall no distance. The y-intercept though of the sample regression line is pretty close to 0, so we're close to having, you know, what it actually could be. Okay, so we've got our alpha and our beta, and now we want to find the standard deviation. Our estimate for the standard deviation, sigma of flight times, about the true regression line is that point. So here you can see the standard deviation of the residuals, S, is 0.168. So S is the standard deviation of the residuals. And we've talked about that before as well. Okay, so this is also the size of a typical prediction error if we use the least squares regression line to predict the flight time of a helicopter from its drop height. So now we've got our alpha, our beta, and our sigma approximates, basically. So let's return to our earlier exploration of the Old Faithful eruptions. For all 222 eruptions in a single month, the population regression line for predicting the interval of time until the next eruption from the duration of the previous eruption is given by this equation, and the standard deviation is 6.159, the population standard deviation. If we take all possible simple random samples of 20 eruptions from the population, we can get the actual sampling distribution of B. So we can see normal, we can see the center, we can find the spread. And in practice, we don't know sigma. So we estimate it with the standard deviation of the residuals. And I don't know when you've ever had to do this by hand ever on an AP test or a test for me, but you need to identify it from the Minitab output. So let's transform some of these values. When we have our z-score, we know it's the actual minus the predicted over the standard deviation. So let's replace some of this. When we have t's, because we don't know the actual population standard deviation, so instead of having a z, we're going to have a t. And since we don't know sigma, we can replace it with the standard deviation of the residuals. So the figure shows the result of standardizing the values in the sampling distribution of B from the Old Faithful example. Recall that n was 20 for this example. And the superimposed curve is a t-distribution, and we do n minus 2 degrees of freedom for this guy. I know, lots to remember with degrees of freedom. But now when we're doing with the least squares regression line, our degrees of freedom are going to be n minus 2. So constructing a confidence interval, just like before, we have our statistic plus or minus our critical value times our standard deviation. So our statistic is going to be our B, plus or minus a critical value of T star, and times the standard deviation of the residual here. So this is a T interval for the slope. And just kind of a reminder, our degrees of freedom is n minus 2 when we're dealing with this. Okay? All of that to get here, right? Remember, B is the statistic for the beta. And here's the standard error for the least squares, for the standard, oh my gosh, for the least squares regression line, for the residuals. Blah, there's that formula again. So T star is the critical value. So let's look at this one again, back to that helicopter. We just saw that. Construct and interpret a 95% confidence interval. And we already checked the conditions, so we don't have to do that again right now, but if we didn't have, if we've never checked them, then we would have to. But we did that just a little bit ago, the Leonard. So if you want to check them again, great, or look back to your notes to kind of add on to this or what you need to. So here we can find our standard error. We can find that we had n was, where are we at? N was 70, so 70 minus 2, we have 68 degrees of freedom. And you can either go to the table, or you could go ahead and put this into your calculator. Let me get my calculator out so I can tell you. Actually, I don't think you can put it in this interval because you don't have the list. You only have the Minitab. So you're definitely going to have to do this one by hand. Sorry about that. Okay. Yes. So you can look at that test in your calculator, but this one you need to get out by hand. So you're going to do your B plus or minus your critical value times your standard error. So we have our b, remember this would be y hat equals negative 0.03761 plus 0.005724 okay? So there's our slope, there's our b. I know b, you always are like, y-intercept, but not with the a and the b. It's not mx plus b, it's a plus bx. So there's our b, getting our critical value from looking at our table with our degrees of freedom. And it was at a, what was it? Was it 95? 95%, so go up from 95% and over from a degrees of freedom of 68. Oh, and you have to always round down in your table. So you have to go to 60 because they don't have 68 in your table. So you get that T star of 2. And doing your math. Here's your standard error for B. So here we are 95% confident that the interval from the two values and seconds per centimeters captures the slope of the true regression line relating to the flight time and the drop height x of paper helicopters. All right, so let's try this one. In Module 3, we examined data from a study that investigated why some people don't gain weight even when they overeat. Perhaps fidgeting and other non-exercise activity explains why. Researchers deliberately overfed a random sample of 16 healthy young adults for 8 weeks. They measured fat gain in kilograms and change in energy use in calories from activity other than deliberate exercise for each subject. Here are the data. Construct and interpret a 90% confidence interval for the slope of the population regression line. All right. So here we're going to do a t interval because we do not know sigma. So we're going to do a t interval for the slope to estimate beta. The population slope. We got to check our conditions. So we need to go to linear. The scatter plot shows a clear linear pattern, and the residual plot shows a random scatter points around 0. Independent. So we went without replacement, so we need to do our 10% rule. So we have to say that there are at least 160 healthy young adults in the population of interest here. Normal, the histogram looks a little bit skewed right, but pretty normal. Equal variance, it's hard to tell from this so few points, but we can see that they are all around 0, okay, in that residual. And random, it said that they were randomly selected. Okay. So here we're going to have n minus 2 degrees of freedom. For a 90% confidence level, we can go find with 14 degrees of freedom from 90 in that table, our t star is 1.761. So now we can put together our slope plus or minus our critical value times our standard error. So going back. Okay. So there's our slope and our standard error. All right, moving forward. So doing all the math behind that and getting to this interval, we can conclude we are 90% confident that the interval from those two values in kilograms captures the actual slope of the whole population regression line relating the net energy activity change to fat gain for healthy young adults. Okay, so performing a significance test for the slope, when the conditions for inference are met, we can use the slope B of the sample regression line to construct a confidence interval for that slope of beta of the population, the true regression line. We can also perform a significance test to determine whether a specified value of beta is plausible. The null hypothesis has the general form that here beta equals the hypothesized value, and to do a test, standardize B to get to the test statistic. So remember, our test statistic is the statistic minus the parameter divided by the standard deviation. So here we have this, this formula you are going to have. You have it on your formula sheet. You need to know this. Okay. To find the p-value, use a t-distribution when n minus 2 degrees of freedom. Here are the details for the t-test for the slope. Okay, so suppose the conditions for inference are met. To test the hypothesis, we're going to compute the test statistic, find that p-value. Okay, so find the p-value by calculating the probability of getting a t-statistic this large or larger and the direction specified by the alternative hypothesis, and use the t-distribution with degrees of freedom n minus 2. So here's an example, crying and IQ. Infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of rubber band on the sole of the foot caused the infants to cry. That's so mean. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the child's IQ at the age of 3 years using the Stanford Binet IQ test. A scatter plot and Minitab outputs for the data from a random sample of 38 infants is below. Please don't do this test at home. Okay, so here's all of this. So do these tests provide convincing evidence that there is a positive linear relationship between crying counts and IQ in the population of infants? Well, let's find out. So we want to perform the test where your null hypothesis, remember, is just that your beta here is going to be 0. So beta is the true slope of the population. And then your alternative hypothesis is that it is greater than 0. Okay. And they didn't tell us the significance level, so we'll do 95% confidence level. So our alpha here will be 0.05. This alpha is a different alpha than what we were doing with the equation. I know. Okay, sorry. So that's the old alpha that we were talking about, not the new one in this module. So if the conditions are met, we're going to perform a t-test for the slope of beta. So is it linear? The scatter plot suggests a moderately weak positive linear relationship. And the residual plot shows a random scatter plot, so linear looks to be a better fit. Independent. Later IQ scores of individual infants should be independent. Due to sampling without replacement, we have to check our 10% condition and say that there are at least 380 infants in the population from which these children were selected. Let's see, linear N. Normal. So let's look here. The residual shows a slight curvature, which suggests the responders may not be normal over at that right-hand graph. With such a large sample size, however, the T procedures are robust, so N is greater than 30, we're good to go. Equal variances. The residual plot shows a fairly equal amount of scatter around the horizontal line, top and bottom, and are random. It's told that they were randomly selected. All right. So, with no obvious violations of the conditions, we can proceed. Here's the Minitab. So here it tells us what our t value is going to be when we're using our b's going on. So that's the t, that's all for this variable for the b. So I have a slope of 1.4929. We said that our hypothesis, our beta was going to be 0, and we're going to divide by that standard error, 0.4870. And here we can see our t, which they gave us, was 3.07. So like I said, that's almost always going to be given to you. I can't remember when it wasn't in the question. All right, so the Minitab also tells us that p-value, 0.004 is the p-value of a two-sided test. So the p-value for the one-sided is going to be half of this. So that's the overall. So this we just conducted. Remember, our alpha was just it wasn't not equal to, so it's a one-sided test. So we have a p of 0.002. So now we can compare our p to the alpha. 0.002 is less than our significance level here. So we have enough evidence to reject the null and conclude that there is a positive linear relationship between the intensity of crying and IQ scores in the population of infants. Crazy. So if you ever have a kid when you're older and it cries a lot, it might be because they're really smart. Or it might be because they're hungry or you need to change their diaper or... Okay. Regression and testing slope. Almost done. Hypothesis, null is that the slope is 0. There is no relationship. And the alternative is that the slope is not equal 0. There is a relationship. Okay? So it could be greater than, less than, not equal to. So here are test statistic, slope of the regression, degrees of freedom, and you can always find P using the TCDF. Don't forget some of those things. All right? If you would like to do it in the calculator, if you are giving lists and you're finding the whole y-hat part. So if you have the list, you can do this. If you don't have the list, then you would have to do it all out by hand. Okay? So here's one for you. This one we could do in our calculator because we have the two lists. Lamb's quarter is a common weed that interferes with the growth of corn. An agriculture researcher planted corn at the same rate in 16 small plots of ground and weeded the plots by hand to allow a fixed number of Lamb's quarter plants to grow in each meter of corn row. The decisions of how many of these plants to leave in each plot was made at random. No other weeds were allowed to grow. Here are the yields of corn, bushels per acre, in each of the plots. What is the equation of the least squares regression line for predicting corn yield from the number of Lamb's quarter plants per meter? Define all variables. Then part B, do these data provide convincing evidence that more weeds reduce corn yield? All right, so go put those into your list. And here, part A, you can see that the predicted corn yield, or you could say corn yield hat, okay, whichever you want to say, you can put it in words. It's going to be 1.66.483333 minus 1.92349 weeds per minute. All right, so now part B, that's the harder. We wanted to perform a test at alpha equals 0.05, where we're going to do a t-test for slope. Okay, so here our null hypothesis is beta equals 0. Our alternative is beta is less than 0, where beta is the true slope of the population regression line. Make sure you always define what beta is. I think I forgot to mention that last time. Okay, don't forget you always have to define your variables in your hypothesis. Okay. Scatter plot is approximately linear. Due to the random assignments, we can view as independent. A histogram of the residuals is mound shaped and looks approximately symmetric. Equal variance, if you look at the residual plot, and you should be looking at all of these to make sure you agree. It shows roughly linear or roughly equal scatter for all the x values, and it said it was random. So now we can put this into our calculator. We can do that ln reg t-test because we had the list 1 and list 2. I got my test statistic to be negative 1.9 and a p-value of 0.07. So now we can say since our p-value is less than 0.05, 0.07, let me put that into your list. I'm going to go back and do it really quick. All right. Stat, edit, clear, clear. So you put it in yours, I'm going to put it in mine. $166.7, 72.2. Okay. Stat calc. Let me do my linear regression, make sure I agree. All right, that looks good. So stat tests, linear regression test, list 1, list 2. Yeah, so this p-value was when it was a not equal to. So our p-value, when we can put it into our test, that's like if you went and looked at the chart. So when we, so let me go back so I can tell you a little bit better. So when you did the ln-reg t-test and you had, oh no, hold on, stat test, the linear regression t-test, when you do list 1, list 2, frequency is always 1, and when you have your beta, we chose less than 0 because from our hypothesis less than 0. If I had chose equal to 0 and hit calculate, I would have gotten that for my p-value, and then you'd have to divide by 2 because it's a one-sided. But if I just choose my beta already to be less than 0 and hit calculate, our p-value is half of that amount, which is 0.037499. Now 0.03 is now less than 0.05. Okay, that's what I thought, but I wanted to double check. So we can reject the null and conclude that there is convincing evidence of a negative linear relationship between weeds per meter and corn yield. So summary of the 12.1. So standard error of the slope. I think I accidentally said standard deviation of the residuals. That's your standard area for your slope, B. If I did, come tell me. It's been a long day. Okay, and here's the rest. Yep, we'll be starting 12.2 next, and that will be your last section of notes. Yay! All right, have a good night, or morning, or whenever.